Good evening, and welcome to the Song of Urania, a podcast about the history of astronomy from antiquity to the present, with new episodes every full moon. My name is Joe Antonini. Last month, we started our tour of the astronomy of ancient China by looking at the place of astronomy in Chinese society, particularly elite society, and then turned to the oldest written record of astronomical activity we have in China, the story of Shi and Ho. This month, I wanted to turn to the cosmological systems that developed in the early Imperial period, along with some general characteristics of the calendars, which were, after all, one of the main reasons that astronomers commanded such a high rank in the Chinese state. But before we do get into these early cosmological systems, I wanted to say just a few more words about how the role of astronomy in Chinese society evolved during the Imperial period. Now, in last month's episode, I talked at some length about how astronomy in China was intimately tied to the state. The emperor funded a coterie of astronomers and gave them a mandate to observe the heavens. As a civilized activity, it flowed forth from the emperor, just like all the other fruits of civilization. This relationship between astronomy and the state goes back as far as we can tell in Chinese history. By the time the earliest relevant records start to appear in the Chu dynasty, this relationship not only exists, but seems to have been regarded as an ancient practice. But in the ancient period, emperors were on the whole pretty weak, and Chinese political theory still hadn't come to a consensus, whether voluntarily or not, as to what the role of the emperor should be. But after Ying Zheng conquered the other 5 kingdoms of China, and thereby brought about the start of the Imperial Era, over the centuries, with some ups and downs, the emperor's court expanded and became more formalized. Now, in the 2 millennia that Imperial China spanned, the precise details of the organization of the astronomers within the imperial bureaucracy varied. The name of the unit in the imperial org chart for the astronomers changed fairly regularly, for instance, but often had a fairly literal name, something that might translate as Astronomical Bureau or Astronomical Directorate. But there were a few common features of the organization that generally persisted over all these years. The first was that being within the emperor's astronomical bureau was always a high status position, especially so for those at the head. A corollary of this was that during the reign of most of the emperors, this organization was independent of any other departments within the bureaucracy. The head of the Astronomical Bureau, or whatever its name of the day was, would report directly to the emperor, rather than being managed by some intermediary. The 19th century Austrian sinologist Franz Kühnert wrote tongue-in-cheek, quote, "Probably another reason why many Europeans consider the Chinese such barbarians is on account of the support they give to their astronomers. People regarded by our cultivated Western mortals as completely useless. Yet there they rank with heads of departments and secretaries of state. What frightful barbarism." End quote. The department itself was headed up by 2 individuals. The more important of the 2 had the title of Feng Shuangxi, which is usually translated as Imperial Astronomer. The Imperial Astronomer was ultimately responsible for reporting on the state of the heavens and setting the calendar, which included marking the divisions of the 4 seasons by measuring the solstices and equinoxes. This was the most prestigious position and was generally a hereditary office passed down from father to son. The book The Chu Li, which translates to Record of the Rights of the Chu, written around the 2nd century BC, describes the duties of the imperial astronomer as follows. Quote, "He concerns himself with the sidereal revolution of Jupiter, the 12 months, the hours of the day, the week, and the positions of the lunar mansions. He distinguishes them and orders them so that he can make a general plan of the state of the heavens. He takes observations of the sun at the winter and summer solstices, and of the moon at the spring and autumn equinoxes, in order to determine the succession of the 4 seasons." End quote. The second most important position in the astronomical bureaucracy held the title of Pao Cheng Shi, which is usually translated as Imperial Astrologer. As the name implies, the Imperial Astrologer's role was more focused on divining the implications that changes in the heavens had for matters of state on Earth. Though somewhat more prosaically, another major responsibility of the imperial astrologer was to keep the astronomical records. The Chu Li describes his role like this. Quote, "He concerns himself with the stars in the heavens, keeping a record of the changes and movements of the planets, the sun, and the moon, in order to examine the movements of the terrestrial world, with the object of prognosticating good and bad fortune. He divides the territories of the 9 regions of the empire in accordance with their dependence on particular celestial bodies. All the fiefs and principalities are connected with distinct stars, and from this their prosperity or misfortune can be ascertained. He makes prognostications according to the 12 years of the Jupiter cycle, of good and evil in the terrestrial world. From the colors of the 5 kinds of clouds he determines the coming of floods or drought, abundance or famine. From the 12 winds he draws conclusions about the state of harmony of heaven and earth, and takes note of the good or bad signs which result from their accord or disaccord. In general, he concerns himself with the 5 kinds of phenomena, so as to warn the emperor to come to the aid of the government, and to allow for variations in the ceremonies according to the circumstances." End quote. In addition to these 2 chief positions, there were a couple of other roles of note within the Astronomical Bureau. There was the Shi Chen, which we might translate to something like Imperial Meteorologist, whose focus was more on keeping track of weather patterns, although this use of the term meteorological somewhat resembles Aristotle, since it included other transient phenomena in the heavens like comets or even eclipses. There was also the Qi Hu Shi, which we might translate to Imperial Timekeeper, and was responsible for managing the water clocks. To support all of this work, the Astronomical Bureau employed a staff of hundreds of astronomers who specialized in various tasks, from being the ones to actually make the observations, to timekeeping, marking the calendar, doing mathematical calculations, or making instruments. Additionally, the Astronomical Bureau could make use of an observatory. And what's more, throughout much of Imperial China, the astronomers had not just 1, but 2 observatories at their disposal. One of these observatories was located within the Imperial Palace, and the other was some distance outside. To ensure that the data that the astronomers collected was trustworthy, data collected from each observatory would be compared to the other, and only if the 2 observations agreed would the data be recorded. So we see from a relatively early time that some amount of skepticism was applied to observational data in Chinese science. Now, while this was a good way to structure the data collection process to reduce the chance of mistakes, like any system, it was not infallible, particularly when scientific fraud was involved. By the 11th century AD, the standards within the Astronomical Bureau had become, shall we say, lax. An astronomer named Feng Cheng was appointed to the post of imperial astronomer, and was apparently the first imperial astronomer in some time to take his job as an actual astronomer seriously. As Feng Cheng was taking stock of the procedures of the astronomers he was now responsible for, he became alarmed at what he saw. Apparently, rather than checking to see if the observations between the 2 observatories agreed, and rejecting data that did not, the 2 observatories were just copying each other's records. To make matters worse, they generally did not even bother to make any observations at all. To record the positions of the planets, they would just use a rough algorithm to calculate where the planet should be, rather than actually observing it for themselves. After taking over, Feng Cheng had 6 astronomers punished and tried to instill better standards in the remaining astronomers, but apparently felt that he did not make much progress. His successor, Shen Kuo, was another capable astronomer and bemoaned the poor quality of the astronomers that were under him. To try to find astronomers who knew more about astronomy, he tried to get the entrance exam to the imperial bureaucracy to incorporate more astronomy. He did indeed succeed in getting more astronomy questions added to the exam, but to his dismay, the examiners themselves knew nothing about astronomy, so they just graded the candidates on the quality of their prose, rather than whether or not their answers made any sense. Now, one thing that should be mentioned is that while astronomy was a prestigious occupation in Imperial China, probably more so than most cultures throughout history, it was by no means the most prestigious place you could be in the Chinese bureaucracy. From the early 1st century AD onward, the top school for aspiring bureaucrats to study at was the Tai Shui, which is usually translated to Imperial Academy. Initially, the Tai Shui offered only 2 degrees, both in the classics, but around 7 centuries later, the university had expanded and began to offer 4 more degrees. One of these, called Ming Xuan, was in mathematics and was the most relevant course of study for anyone hoping to become an astronomer. But the Ming Xuan degree was by far the least popular of the degrees offered at the Tai Shui, because students judged that it was the least likely to lead to a high position in the bureaucracy. After all, even though the emperor employed hundreds of astronomers, the imperial bureaucracy was vast, and the astronomical bureau was just a tiny sliver of the overall organization. That said, astronomy was not the only way that a graduate who held a degree in Ming Xuan could use their knowledge of mathematics. Mathematics was needed for the design of public works and in military engineering. Merchants, of course, needed some amount of mathematics too. But none of these occupations were as prestigious as that of astronomer, and there were, in turn, many more prestigious occupations than that which required no knowledge of mathematics at all. Now, a perhaps ironic consequence of the high status that astronomy held in Chinese society throughout its long history is that it ended up limiting our knowledge of it. Thanks to its proximity to the emperor and its importance for assessing the state of the world and making predictions of what was to come in matters of state, knowledge of astronomy was held as a state secret. In fact, the fundamental role that astronomers had in setting the calendar was seen as one of the essential symbols of imperial power. The nearest analog to this in Western civilization is maybe the authority to mint coins with the image of the monarch. Just as a new Roman emperor would begin replacing the old coins that bore the image of the face of his predecessor with new coins that had his own visage on it, when there was dynastic upheaval in China and a new dynastic line was established, one of the first things that the new emperor would do to assert his authority would be to issue a new calendar. If you recall back to episode 26 when I talked about the relationship between astrology and the Roman state, there are some parallels between the role that astronomy played in both societies. Particular omens could be seized upon by rebels to rally support for their cause. Due to this sensitivity, astronomical knowledge was kept as a closely guarded secret. A 10th century history called the Qiu Tang Shu, or Old Book of Tang, described one of the orders that an emperor issued to ensure that his astronomers would maintain appropriate secrecy. Quote, "In the 12th month of the 5th year of the Kai Cheng reign period, that is 840 AD, an imperial edict was issued ordering that the observers in the imperial observatory should keep their business secret. If we hear, it said, of any intercourse between the astronomical officials or their subordinates and officials of other government departments or miscellaneous common people, it will be regarded as a violation of security regulations which should be strictly adhered to. From now onwards, therefore, the astronomical officials are on no account to mix with civil servants and common people in general. Let the censorate look to it." End quote. So in certain periods, not only were astronomers forbidden from sharing knowledge of astronomy with anyone outside the astronomical bureau, they were not allowed to interact with them at all. This secrecy has unfortunately limited our present-day understanding of what China's astronomers were up to for all those centuries. Astronomical texts and records were generally restricted to government archives, and because only a relatively small number of people needed to access them, there tended to be very few copies of these works. So, when there were accidents, or more commonly purges after a dynastic change, it was unfortunately easy for astronomical works to get lost or destroyed. By contrast, the field of mathematics was much less sensitive. The knowledge was more widespread, and there were many more copies of the relevant works. Consequently, despite its lower status, the textual history of Chinese mathematics is much more complete than it is for astronomy. But one of the more important texts for the early history of Chinese astronomy that did survive is called the Luxi Chunqiu, or Master Lu's Spring and Autumn Annals. The work was an attempt to compile a comprehensive collection of all the knowledge of the day, and is unusually long relative to the other Chinese classics, totaling more than 100,000 words. The work was written shortly before the end of the Warring States period and the establishment of the Qin dynasty. You may recall from last episode that the first emperor of the Qin dynasty, Qin Shi Huang, was an ardent believer in the political power of ideas and wanted intellectual life to be under his control. As part of his project to consolidate Chinese scholarship in his state, one of his officials, a man named Liu Buwei, invited 3,000 scholars to the court and asked that they write down all their knowledge. After the Herculean task of compiling all their knowledge had been completed, Liu Buwei displayed the finished book at the city gate and offered a bounty of 1,000 gold pieces to any scholar who could find even a single error in the work. And indeed, not a single error was found, at least until the modern era, by which point the bounty had long since disappeared. But early texts that did survive, like the Lushi Chunqiu, were the exception rather than the rule. That said, however, the astronomical records themselves tended to fare better than treatises on astronomy, because on the whole there was less that could be found to be objectionable by later emperors in them. So the unusual status that Chinese civilization gave to astronomy turned out to be a real boon for all of humanity, because for centuries, Chinese astronomers kept meticulous records of the heavens, many of which do survive. And for large swaths of history, these are the only records of what was going on in the heavens. You may recall from episode 25 about the Star of Bethlehem that astronomers have wondered whether or not the Star of Bethlehem could have been a supernova or a comet. Well, the only reliable astronomical records we have from this period are Chinese and Korean civilization was in turn heavily influenced by its much larger neighbor to the west. The oldest recorded supernovae almost all come from Chinese records. Over the centuries, Chinese astronomers noted around 20 events that we now know were supernovae, with the oldest being recorded in 185 BC. Well, at the root of all the prestige and mystery of astronomy in Chinese society was the calendar. The astrology and divination were important, of course, but came later. The original motivation that the Chinese had to study the skies, as in every society, was to keep time. Now, there was no single calendar that the Chinese people observed for the 3-odd millennia that we have records. As I mentioned earlier, one of the first things an upstart emperor would do after overthrowing the previous emperor and setting up a new dynasty in its place was to establish a new calendar as a way of asserting his authority. So the details of the calendar changed over the centuries. But throughout all this, there were a few general characteristics that these calendars shared. The first was that as far back as records go, it seems that months began on the new moon. Now, this is quite unusual for ancient civilizations. You'll recall that the Babylonians began their months close to the new moon, but not right on it. They began their month on the first evening that the crescent moon was visible after the new moon. This kind of a system was far more common across societies, and for good reason. You can actually tell when the new month has started just by looking at the moon. You see the moon disappear for a few days during the new moon, and then one evening, there it is again, low on the horizon. And the next month has started. By contrast, starting your month on the new moon itself is quite a lot harder because you can't actually see when the new moon is happening, so it requires a rather sophisticated model of the phases of the moon to get it right. For this reason, it's generally thought that originally, prior to records starting, the Chinese probably began their months on the first evening that a crescent moon was visible, just like almost everyone else. But very early on, Chinese astronomy had become sophisticated enough that it could move from the easier to observe but somewhat more irregular first visible crescent to the more difficult to observe but more precisely defined new moon itself as the boundary between 2 months. Now, because the months of the calendar were defined in relation to the moon, the Chinese then had the age-old problem of any society with a lunar calendar. The number of lunar months does not evenly fit into a solar year. And particularly for an agricultural society, this is a big problem, because the main point of the calendar, the reason that establishing it brought so much authority to the emperor, was that it set out times for planting and sowing. Well, the crops don't really care what the moon is doing, they care about what the sun is doing. So the Chinese solved this problem the usual way, by adding in a 13th intercalary month when the months got too out of sync with the seasons. One of the main sources of variation in the different incarnations of the Chinese calendar was when the year itself began. The oldest records from ancient China indicate that the new year was originally marked around the winter solstice, but it seems that different regions observed different customs, and upon various dynastic successions, the new emperor would make official the custom he was used to in his own land. So the date of the new year bounced between the autumnal equinox and the vernal equinox as well. Moreover, even if two calendars were nominally targeting the same solstice or equinox, they might calculate the start of the new year in slightly different ways. Some, like the Yuan Shu calendar, would start the new year on the new moon, closest to the winter solstice. Others, like the Yin calendar, would start the new year on the first new moon after the winter solstice. About a century into the Han Dynasty, Sima Qian, who is better known as a historian but was also an astronomer in the imperial court, convened a conference of astronomers to reform the calendar, and in 104 BC, Emperor Wu ordered the adoption of the Tai Chu calendar. This calendar defined the month containing the winter solstice to be the 11th month of the year, so the new year was typically the second new moon after the winter solstice, unless the year had an intercalary month, in which case it would be the third. This convention has persisted now for more than 2 millennia to the present day, and the Chinese New Year is the biggest holiday in modern China. One of the features of this definition of the new year is that this new moon is almost always the new moon that is closest to the start of spring in Chinese culture. Now here, there's a bit of a difference between Chinese convention and Western conventions, at least modern Western conventions. Today, in the West, we typically mark the transition between seasons at the solstices or equinoxes. So summer, at least astronomical summer, formally begins on the summer solstice and lasts until the autumnal equinox. The Chinese convention, however, is for the seasons instead to straddle the solstices and equinoxes. So the vernal equinox marks the middle of spring, not the beginning, and the start of spring comes about a month and a half earlier, around early February. In fact, much of Europe used to follow this convention as well, particularly in the north, and we still retain some vestiges of it. The date of midsummer is the summer solstice, which is today not the middle of summer, but its start, but centuries ago was considered to be the middle of summer, hence its name. But of the various calendars in ancient China, the oldest we know of is called the Yuan Shu calendar, named after the legendary emperor Yuan Shu. Supposedly, Yuan Shu introduced sacrifices to soil and grain to invoke a good harvest, in addition to the traditional sacrifices to the ancestors. These sacrifices to soil and grain later came to have important political consequences during the Warring States period, in conjunction with a mandate of heaven. One of the justifications that rebelling kings made for their insurrection was that their loyalty lay first and foremost to the soil and grain, rather than to the ruler himself. Well, the Yuan Shu calendar is said to have begun with a conjunction, or at least some sort of gathering, of all 7 planets in the constellation of Yingxi at dawn on a day in early spring. This would place its nominal start date at February 13th, 1953 BC. The constellation of Yingxi corresponds to the asterism called the Great Square of Pegasus in the west, which consists of 3 stars in Pegasus and 1 star in Andromeda, and as the name implies, forms a great square in the sky. The Great Square is not nearly as famous as the other main asterisms like the Big Dipper and to a lesser extent the Summer Triangle, but once you see it, you can't unsee it. In China, Yingxi was associated with the boar and the porcupine because these 2 lunar mansions overlapped with it. And, perhaps not coincidentally, the grandson of Yuan Shu was said to be Yu the Great, who founded the Xia dynasty and whose symbol was the boar. Yingxi had some other rather poetic names as well: the Ancestral Temple, the 4 Supports of Heaven, and my favorite, the Palace of Darkness. Well, the Yuan Shu calendar was a standard kind of calendar. It marked the months, the new year, the equinoxes, and so forth. The first calendar of a specifically astronomical character comes somewhat later, probably around 350 BC, but possibly a few centuries earlier. This is the Xia Xiao Cheng. It resembled more a farmer's almanac than anything else, as it included notes on the weather and animal migration patterns over the course of the year. But it also included the positions of the most important constellations throughout the year to help the reader keep track of what time of the year it was. It's around this time, too, in the middle of the 4th century BC, that we see records from the earliest astronomers of significance. Or at least the earliest of significance that were not purely legendary, like Shi and Ho from the last episode. These astronomers are Shi Shen and Gan Dai, and their main claim to fame was in compiling the earliest star catalog in China. This star catalog contained around 800 stars in it, making it comparable in size to the star catalog of Hipparchus a few centuries later. Shishen and Gande apparently worked independently, and their individual star catalogs were later merged, probably around 70 BC. Shishen's other main surviving accomplishment is in making the first recorded observation of sunspots, which he described as being like an eclipse that began at the center of the sun and moved outward. Gande apparently produced a substantial body of literature on astronomy in the form of 2 books. The first of these was called Tian Wen Shenzhan, which translates to New Astrological Prognostications of the Patterns of the Heavens, and was 8 volumes long. The other text was called Sui Xing Jing, or the Canon of the Planet Jupiter, but unfortunately both texts were lost, and all we have for them are a few quotations in later works. But from what we do have, Gande seems to have made the first measurements of the synodic periods of the planets, that is, the time from opposition to opposition, and his measurements were passably accurate, being correct to within a few days of their true values, with the exception of Mercury, where he gave 136 days instead of 116. But Gande's most intriguing observation to have survived was his possible observation of Jupiter's moon, Ganymede. One of the later texts quotes him as saying that, quote, "In the year of Chan Yan, Jupiter was in Z. It rose in the morning and went under in the evening together with the lunar mansion Nu, Shu, and Wei. It was very large and bright. Apparently, there was a small reddish star appended to its side. This is called an alliance." End quote. The interpretation that this small reddish star was Ganymede is plausible. Under very good conditions, Ganymede can in fact be seen with the naked eye by someone with very good eyesight, and Gande's description is more or less consistent with what someone seeing Ganymede would observe. Incidentally, Ganymede is not the only such object that could have been discovered before the invention of the telescope. The planet Uranus is also visible to the naked eye, and may actually have been recorded in Hipparchus's star catalog, though it was not recognized as a planet. Well, I next wanted to talk a little bit about ancient Chinese cosmological theories. Over the centuries, there were 3 principal theories, each of which had their various proponents at different times. The oldest of the 3 is called the Kai-Tien theory. The idea was that the Earth was like a bowl turned upside down, and the heavens were a hemisphere sitting on top of it. So in this picture, the universe consists of 2 concentric domes. This was a rather unusual theory among ancient civilizations. It's fairly common to see theories that take the Earth to be flat and the heavens to be a hemisphere sitting on top of it, but I don't know of any other case where the Earth was also taken to be convex. Ursa Major was taken to be at the center of the heavens, and China naturally was in the middle of the Earth, which was also the highest point. Rain flowed down to the edge of the Earth, where it formed an ocean surrounding the Earth. Now, in the Kai-Tien theory, the shape of the Earth was actually not exactly hemispherical. Its edges were straight, forming a square. So the picture is more like one of those bowls you might see at a fancy restaurant that is sort of curved on the bottom but square on the sides. The idea that the Earth was square was also a characteristically Chinese idea. The distance between the heavens and the Earth at China, the highest point, was taken to be 80,000 li. Now, like the Greek stad, the length of the unit of the li is somewhat uncertain and fluctuated fairly substantially over the centuries. But very roughly, a li was about 1/3 of a mile, or about half a kilometer. So in the Kai-Tien theory, the heavens were around 40,000 kilometers above China. Now, another unusual feature of the theory was that because the Earth curved down, as did the heavens, at the lowest point of the Earth, where the great ocean was, the heavens were quite a bit closer, only 20,000 li, or 10,000 kilometers above the Earth. This meant that parts of the heavens near the edges were actually lower than the highest point on Earth. In this model, the rising and setting of the sun and stars was simply an illusion. Nothing actually passed under the Earth. The sun and the stars were simply only visible when they were somewhat close by. Specifically, the sun could illuminate a circle of diameter 167,000 li, or around 80,000 kilometers. The whole of the heavens rotated around like a millstone, which is an analogy that Chinese astronomers frequently invoked. An astronomer named Wang Chung wrote in the Lun Heng, quote, "The sun and moon are attached to heaven, and follow its movements during the 4 seasons. Their movement may be compared to that of ants, crawling on a rolling millstone. The movements of the sun and moon are slow, while heaven moves very fast." End quote. Incidentally, about a century earlier, the Roman architect Vitruvius also made a very similar analogy of the motions of the sun and the planets to ants crawling on a potter's wheel. Well, because the sun and stars never went below the Earth in this model, since there was nothing below the Earth, the only reason they appeared to set was that they simply got too far away to see. Here, Wang Chung made another analogy, that it was like a man walking off into the distance on a level plain while holding a torch. As he recedes, the torch becomes fainter and fainter until it's not visible at all. So it was with the sun. When it moved to one edge of the heavens in the evening, it eventually disappeared from sight. Now, later opponents of this theory seized on the same analogy to argue why this theory must be wrong. After all, when we see a sunset, it doesn't really look like the sun is moving off into the distance and gradually getting fainter. It's not getting smaller and fainter. If anything, it appears to get a bit larger on the horizon, and it does literally look like it is going under the horizon. Well, proponents of the Kai-Tian theory never really had good answers to these objections, and by the Han Dynasty, serious astronomers had moved on to more plausible cosmologies. But as the oldest theory, it nevertheless remained influential in a society that prized tradition. One of the questions that early astronomers in this school raised was why the polar axis seemed to be inclined. We observe that the stars revolve around the North Star, but in China, the North Star is at an altitude of about 40 degrees. If China is at the center of the Earth, wouldn't it be more natural if the heavens revolved around the point directly above the Earth's center, so that the North Star was directly overhead? An astronomer named Yao Xin, in the middle of the 3rd century AD, argued that the tilt of the polar axis was evidence that there was a second Earth. This lower Earth was what supported the celestial axis. In an analogy to the human head, the upper Earth was like the top of the head, and the lower Earth, which supported the heavens, was like the chin. But as with a head, the chin cannot be right on the bottom. It has to jut forward a little bit. So that was why the polar axis had to be somewhat tilted away from vertical. The last detail of the Kai-Tian theory that I'll mention is that the polar axis was seen as a kind of pole that the heavens slid up and down along. So during the summer, the heavens slid up the pole and were actually somewhat farther away from Earth, and during the winter, the heavens slid down the pole and were somewhat closer. The next major cosmological theory is called the Han-Tian school, or the theory of the celestial sphere. As the name implies, the idea was that a great sphere surrounded the Earth and the planets and stars were embedded onto this sphere. The idea of a celestial sphere is somewhat implicit in the coordinate systems used by Shishen and Gande in their star catalogs, but the first real description of the cosmological system comes in the 1st century AD. In this theory, the diameter of the sphere is taken to be 2,032,300 li, which is around 1 million kilometers. But calling it the celestial sphere theory is a slight misnomer, since the theory actually held that the heavens weren't perfectly spherical. They were actually 1,000 li shorter in the north-south direction than in the east-west direction. This sphere was said to be held together by some sort of a bond. The astronomer Chang Heng described the theory as follows in the Han Yi Chu. Quote, "The heavens are like a hen's egg, and as round as a crossbow bullet. The earth is like the yolk of the egg, and lies alone in the center. Heaven is large, and the earth small. Inside the lower part of the heavens there is water. The heavens are supported by vapor. The earth floats on the waters. The circumference of the heavens is divided into 365¼ degrees. Hence half of it, 182 5/8 of a degree, is above the earth, and the other half is below. This is why, of the 28 lunar mansions, only half are visible at one time. The two extremities of the heavens are the north and south poles. The former, in the middle of the sky, is exactly 36 degrees above the earth, and consequently a circle with a diameter of 72 degrees encloses all the stars which are perpetually visible. A similar circle goes around the south pole and encloses the stars which we never see. The rotation goes on like that around the axle of a chariot." End quote. Now, we see from this description that this theory wasn't quite like Aristotle's conception of the universe, with the Earth as a sphere surrounded by the spheres of heavens. Here, the Earth and the heavens are indeed spherical, or nearly so, but the Earth is nevertheless floating on water, so the lower half of the sphere of the heavens is filled with water. Now, in contrast to the earlier Kai-Tien theory, the Han-Tien theory held that the sun really did go beneath the Earth during the night. But proponents of the older Kai-Tien theory argued that the theory of the celestial sphere was implausible on its own terms, because it implied that the fiery sun was doused in water as it traveled underneath the Earth every night. In reply, the astronomer Ko Hung argued that the sun was analogous to dragons, which are fiery by nature but can nevertheless live in the water. Well, despite some of these quirks, by the end of the Han Dynasty, the Han-Tien school had become the dominant cosmological theory. The final cosmological theory that had some influence was called the Xuan-Ye theory, and seems to have been associated with Taoism. The Xuan-Ye theory was not nearly as influential as the Han-Tien school, but the Han-Tien school may have been influenced by it. Rather than describing it myself, we can turn to a later description of the theory by Ge Hong, who was writing in the early 4th century AD. Quote, "The books of the Xuan-Ye school were all lost, but Qi Meng, one of the librarians, remembered what its masters before his time had taught concerning it. They said that the heavens were empty and void of substance. When we look up at it, we can see that it is immensely high and far away, having no bounds. The human eye is colorblind, and the pupil short-sighted. This is why the heavens appear deeply blue. It is like seeing yellow mountains sideways at great distance, for then they appear all blue. Or when we gaze down into a valley 1,000 fathoms deep, it seems somber and black. But the blue of the mountains is not a true color, nor is the dark color of the valley really its own. The sun, the moon, and the company of the stars float freely in the empty space, moving or standing still. All are condensed vapor. Thus the 7 luminaries sometimes appear and sometimes disappear, sometimes move forward and sometimes retrograde, seeming to follow each a different series of regularities. Their advances and recessions are not the same. It is because they are not rooted to any basis or tied together that their movements can vary so much. Among the heavenly bodies, the pole star always keeps its place, and the Great Bear never sinks below the horizon in the west, as do the other stars. The 7 luminaries all fall back eastwards, the sun making 1 degree a day, and the moon 13. Their speed depends on their individual natures, which shows that they are not attached to anything, for if they were fastened to the body of heaven, this could not be so." End quote. This picture of the universe as a vast void in which the heavenly bodies are floating about is really quite advanced for its time. Another proponent of the theory, Yu Shi, described it around the same time like this, quote, "I think that the heavens are infinitely high, and that the space below the earth is unfathomably deep. Undoubtedly, the form of the heavens above is in a permanent state of rest, and the body of the earth below also remains quiet and motionless. One envelops the other. If one is square, so is the other. If one is round, so must be the other. They cannot differ as to squareness and roundness. The luminaries are distributed, each pursuing its own course, like the high and low tides of the sea and its rivers, and like the thousands of living creatures which sometimes come out and sometimes hide away." End quote. Particularly in later descriptions of the theory, the motions of the sun and the planets are said to be due to the forces of a hard wind that blows the celestial objects about. By the time we get to the 11th century, Chinese astronomers were taking this theory seriously enough that there was some discussion around the specific physics of this hard wind. Now, although the overall picture of the universe is quite congruent with that of modern astronomy, the main shortcoming of the Xuan-Ye theory at the time was its inability to really make any quantitative predictions, and certainly any quantitative predictions that would distinguish it from the model of the celestial sphere. But this was actually a broader issue with Chinese astronomy in general. One of the great scholars of Chinese science, Joseph Needham, argued that Greek and Chinese astronomy had opposite shortcomings. In the case of Chinese astronomy, The fundamental shortcoming was that its geometry was underdeveloped, so that it was difficult for Chinese astronomers to connect their extensive observations to any underlying theory that was more sophisticated than simply extrapolating from historical patterns. By contrast, the main impediment to the development of Greek astronomy was a kind of obsession with geometry to the detriment of its connection to observation. Greek astronomers were willing to entertain highly elaborate models of celestial motion, but were less interested in the physical character of these models. So long as they produced the correct motions of the planets, the Greeks were satisfied. Well, despite the relative prestige of astronomy in Chinese society, the attitude of Confucians to questions about the nature of the heavens tended to be one of indifference. There's a tale written in the Liei Tzu, sometime between the 4th and 1st centuries BC, that illustrates this kind of apathy. It goes like this. Quote, "When Confucius was traveling in the East, he came upon 2 boys who were arguing, and he asked them what they were arguing about. One said, 'I believe that the sun is nearer to us when it is rising, and that it is farther from us at noon.' The other said, 'I, on the contrary, believe that the sun is farther from us when it is rising and setting, and that it is nearest to us at noon.' The first boy replied, 'When the sun is rising, it looks to be as large as a chariot roof, but at noon the sun appears to be no bigger than a plate. That which is large must be near us, while that which is small must be further away.' But the second boy said, 'At dawn the sun is cool, but at noon it burns, and the hotter it gets, the nearest it must be to us.' Confucius was unable to solve their problem. So the 2 boys laughed at him and mocked him, saying, 'Why do people pretend that you are so learned?' End quote. This story is in a genre associated maybe unsurprisingly with Taoism, in which 1 or 2 small boys or an old man defeats Confucius in argument. But the broader point in the story is that the Confucian tradition was very interested in the role that astronomy played in society, and maintaining social order by setting the calendar and so forth. But the Taoist criticism was that the Confucians weren't so interested in astronomy as such. Just as they didn't spend much effort pondering the supernatural, they didn't spend much effort pondering abstract questions about the natural world. If we look at another predecessor of the modern sciences, alchemy, it's perhaps not a surprise that it was mostly associated with Taoism, and was not practiced in polite society. Alchemy lacked the cultural cachet that astronomy had, and so it was essentially ignored by the orthodox schools of thought in Chinese intellectual culture. And it probably didn't help that it was a messy, grubby business where you'd have to get your hands dirty. But this is not a history of alchemy, this is a history of astronomy, so I think I will leave things here for this month. Next month, we will look at the Chinese theories of eclipses and planetary motion, along with the role of the lunar mansions, the Xiu. Then we may skip ahead a little bit and talk about one of the more interesting encounters between Eastern and Western science when the Jesuit missionaries arrived in China in the 16th century. I hope you'll join me then. Until the next full moon, good night and clear skies.